Wonderful. Okay. So thank you very much, everyone, for joining us for the Early Career Mathematicians seminar. Today we have Claire to talk about mathematics and modelling better than watching paint dry, as you can see on the screen. So Claire is the winner of the IMA Lighthill Thwaites Prize. So for those of you who are not sure what that is, Lighthill and Thwaites are the first two of the IMA's president. And the Lighthill Thwaites Prize is a biennial prize for mathematicians who produce research and supplementary then present it at the British Applied Mathematics Colloquium. It's a conference in the UK, a small 3-day conference. This year it was hosted in Bristol, and next year it's going to be hosted in next year it will be hosted in Newcastle. So the prize is every 2 years and you have to submit for it. So if you are an early career mathematician, you've produced some really research that you're proud of and you think that it could be for the prize, then do keep an eye on the IMA webpage. My name is James, which is probably what I should have started with. I'm the events leader for the Early Career Mathematicians Committee. I'm joined by Jack, who's our communications leader, or our engagement leader, I think is the technical term for it. The Early Career Mathematicians Committee is, we are like elected people who are in charge of trying to facilitate events for early career mathematicians, trying to lobby the IMA for better prospects for early career mathematicians. If you want to know more about what we do, the events that we run, have a look on the IMA webpage. I'll put a link to us and our webpage in there shortly. Please do feel free to email me if you are interested in maybe joining the Early Career Mathematicians Committee or just wanting to learn more. We will be hosting elections to replace some individuals. Normally they happen in December and January. So do keep your eyes peeled if you're interested. So enough from me. I will hand over to Claire now.
Thanks, James, for the introduction. I was going to start by telling a little bit about me. I did my undergrad and PhD in Cambridge in chemical engineering. The photo here is of me at Trinity College, Cambridge, looking very excited with some Molly Mod kit. Then about a year ago, I moved to Oxford, where I started a junior research fellowship at Christchurch. We're having a really good year, and I've got up to 2 or 3 more years here. The work that I did in this talk is what I did during my PhD. So I'm going to be telling you about paint drying. I'll start with an introduction about why I'm interested in paint drying. Then I'll go on to a basic model of a drying film. It will include talking about a phenomenon called diffusophoresis, but don't worry if you haven't heard about that before, because I will explain what it is. Then I'm going to show an experiment which I did to try to determine what are the important phenomena that we should be modelling in a drying film. And I'll end by putting this all together to answer the question of how we can control paint drying. So I'm imagining a system where I've got particles of 2 different sizes, so black and white particles, and a solvent, which is in blue. Over time, the solvent evaporates. Now, a variety of different particle arrangements are seen in dried films, but it's often seen that small particles accumulate at the top surface, which you might be able to make out in this cryo-SEM image. So you might be able to see that there's an excess of small particles at the top surface. It isn't fully understood why this should occur, so my work's been seeking to explain this, the aim being that then we could engineer the drying process such that particles end up exactly where we wish. On this slide, I have some examples of applications where this would be useful. So it could be in cases where we only really need an expensive component to be located in a certain part of the film for it to do its job. So it would be cheaper if we only put in enough for this component to cover the top surface. So that's things like biocidal coatings and catalyst coatings on catalyst pellets. Then I've got an example of layered car paints. So the coating on cars isn't just one layer, it's many layers, which are sprayed on currently one at a time, and then you'd have to wait in between for each one to dry. It'd be much faster if we could spray on, say, one layer and the particles separate out themselves. A final example is a kind of 3D printing where we get the particles to end up in their final positions through the drying process. So I'm going to briefly discuss some key mechanisms that are going to be included in my models. Firstly, diffusion, which you're very likely familiar with. This is where particles move down their own concentration gradient. We can describe it with Fick's law, where the flux J is proportional to the concentration gradient, and the constant of proportionality is the diffusion coefficient, D. Diffusophoresis is analogous. This is where particles move up or down the concentration gradient of a different particle type. Something similar to Fick's law, we've got a flux J proportional to the concentration gradient of the other particle type. We have a constant of proportionality gamma, which is we call the diffusophoretic drift coefficient, and that can be either positive or negative depending on the mechanism or depending on the direction in which our particles go in a concentration gradient of the other particle type. Diffusophoresis can be caused by different physical processes, some of which I'll introduce later in the talk. Then I want to discuss how might we model the phenomena that are happening in our drying film. One option is molecular dynamics, where we model every single particle, say of each size in our drying film. This, as you can probably imagine, is very computationally intensive. We could go further and we could, in addition to modeling every single particle, we could also model all the solvent particles, which we call explicit solvent method. And this is even more computationally intensive, although molecular dynamic models are very useful in terms of their likely high accuracy compared to reality. Another approach would be a continuum approach, whereby we solve for the concentration profile of each component. We could make, say, a one-dimensional model. This is the approach I'm taking in this work. It allows me to form equations where we can link terms in the equations to the phenomena to try to determine which phenomena are contributing to the results. It also allows us to do some nice maths with the equations, and it's easier to solve computationally, relatively compared to molecular dynamics. As having to introduce you to why I'm interested in paint drying, I'm going to show you a basic model of the process. This section is work that's published in this JFM paper, which is the paper for which I won the we're very lucky to be awarded the IMA Lighthill Thwaites Prize earlier this year. So on this slide, I have an imagined animation of a process where I've only modeled diffusion and evaporation. Initially, the top surface is at height h, but the top surface descends over time, and the particles therefore become closer together until they would become close packed. There's a playoff here between diffusion and evaporation. Particles which can't diffuse fast enough would be trapped by the descending top surface, whereas particles which can diffuse faster can spread further down the film. We characterize this playoff by the dimensionless group, the Peclet number, giving the ratio of evaporation to diffusion based on the Stokes-Einstein diffusion coefficient, D. You'll note that D is inversely proportional to the particle radius. So we'd therefore expect that larger particles would diffuse more slowly, and so would stratify to the top surface. But then you'll see that this wouldn't explain our experimental observations of small particles stratifying to the top surface, which suggests that we may need to include some other phenomena in our model. To start with, though, I'll just model diffusion, but then we can later discuss adding other phenomena. So I've written down a conservation equation for the volume fraction phi of each component I, where I would be 1 or 2 in a mixture of 2 different particle sizes in solvent. The diffusive flux N for each component is found by summing over the Fick's law contributions for from each component in the mixture. A key problem was that the Stokes-Einstein diffusion coefficient was originally derived for a single particle diffusing in infinite solvent. But here we have a multi-component concentrated solution. My solution to this was to write the diffusive flux as shown, where you see I've invoked these coefficients K, which we call sedimentation coefficients, by analogy with sedimentation. We have, they account for hydrodynamic hindrance. We have analytical expressions for dilute solution only for these sedimentation coefficients, but we can extend them to functional forms which also seem physical for more concentrated dispersions. We also need chemical potential expressions that are valid up to close packing. It's because our film goes from dilute to concentrated to close packed over the course of drying. I did this by relating the osmotic pressure pi to the compressibility Z. The equation here is pretty much just the ideal gas law, pi equals NKT, or modified by this compressibility Z. Mu S is the chemical potential of the solvent. Mu S naught is the solvent reference chemical potential. Mu S is the volume of one molecule of solvent. Then I relate the chemical potentials in the system together using the Gibbs-Germ equation. So this slide summarizes the equations from the previous 3 slides, which I'll put together to form some PDEs to describe the diffusion process. I put together the conservation equation, the diffusive flux, chemical potentials, the Gibbs-Germ equation to derive equations that should be valid for concentrated dispersion. I also include in this model a certain type of diffusophoresis, which is called excluded volume diffusiophoresis. That's because this was hypothesized that it may be what's causing the accumulation of small particles at the top surface. I wanted to test this. So excluded volume diffusophoresis is relevant in mixtures of particle sizes, where the small particles are excluded from a certain distance around the edge of each of the large particles. You can imagine having a tennis ball and a football, and you cannot physically get the center of the tennis ball past one radius away, tennis ball radius away from the edge of the football, simply because they would overlap. And this is what this effect is. By geometry, for hard spheres, we would expect the excluded distance, which I've labeled RdP, to be equal to R1, the radius of the small particles. But I'm going to explore what happens as RdP is varied. So that's varying the strength of diffusophoresis. I include diffusophoresis in my model by adding another flux term, J, with a diffusophoretic drift coefficient gamma, and it's the J is proportional to the concentration gradient of the small particles. So having derived some PDEs, I non-dimensionalize them, giving me dimensionless time and dimensionless space, and a dimensionless group for each particle type. That's the Peclet number. I then transform the coordinate system. That's because in the non-transform system, the top surface is descending due to evaporation, and that's problematic for a numerical solution because the boundary condition is a moving boundary. I therefore have a coordinate transform to a frame with fixed boundaries, giving me new coordinates of tau and psi. I solve the resulting equations numerically using a finite volume method because this naturally conserves particles. And I finally verified the code with asymptotic solutions, which I'll show you in a bit. On this slide is some example model results. So firstly, the diffusion only model. On the y-axis is the volume fraction of each particle type. And on the x-axis is the scaled height up the film. So the top surface is the right-hand side of the graph. That's the gray line showing the solvent-air interface. At time 0, the concentration profiles for each component are flat. We're starting off with the homogeneous mixture. In red, I show the small particles, and in blue, I show the large particles. These are example results for Peclet numbers straddling 1. So in these examples, diffusion and evaporation are roughly similarly important. Then I show you what the profiles look like at a later time. You see that the solvent interface has receded inwards due to evaporation. At the top surface, the right-hand side of the graph, we see that the films become more concentrated. And we see that the top surface, the blue line is above the red line. which is showing a prediction of large on top stratification, which is what we'd expect from a diffusion-only model. Further down the film, the profile's still pretty flat because it's not yet affected by what's going on the top surface. I've added on a few more lines here for later times, and we can see this large on top stratification developing. So next, I add excluded volume diffusiophoresis to the model. You now see that the red and blue lines are pretty much on top of each other. So this is predicting a uniform film. It's suggesting that excluded volume diffusiophoresis is acting against large on top stratification. I then see what happens if I increase the excluded distance around each of the large particles. So this is strengthening excluded volume diffusiophoresis. You'll now see that at the right-hand side of the graph, the red lines are above the blue lines. This is showing prediction of small on top stratification. So it's further supporting that excluded volume diffusiophoresis could be causing small on top stratification. On this slide, I have some results higher Peclet number. That is a fast evaporation compared to diffusion. You'll now see that at the right-hand side of the graph, the red line is much higher than the blue line. So it's predicting a strong small on top stratification, suggesting that fast evaporation could be a way to obtain this strong stratification. You'll also note that it starts to look like these concentration profiles are attaining a constant shape moving across the film over time. This is the inspiration for deriving an asymptotic solution. I did this by noting that there are two key transitions in the profile, which I've labeled here as P and Q. P is the diffusion evaporation front, and Q is a kind of diffusion diffusiophoresis front. I make a coordinate transform to a variable x, which is an expansion about P of tau. I then, in brief, I solve for the concentration profile around P of tau and around Q of, and well, the values either side of Q tau. So in the lighter colors, I've shown the asymptotic solution, and you see that it's very close to the numerical solution. So it verifies the numerical code. To summarize this section, we've seen that a diffusion-only model predicts large on top stratification. And then if we add an excluded volume diffusiophoresis, we predict small on top stratification and increasingly as we increase the strength of diffusiophoresis. So having made a basic model for a particular type of diffusiophoresis and diffusion, I then going to show experiments which addresses the question of what are the relevant phenomena to be modeling in a particular system. I'm going to be looking at a dispersion of latex and silica particles, which are commonly found in industrial coatings. So I run an experiment in a Healy-Shaw cell, named after Mr. Healy-Shaw, and this is parallel plates a few millimeters apart. It's commonly used for studying laminar flow. I set it up with a background gradient of small particles, which I've dyed red here for illustration, although in practice the camera can't see the small particles that I use. Into this background gradient, I'm going to add a thin layer of big particles. And I want to determine the magnitude of the diffusiophoretic flux of these larger particles. If the large particles were not affected by the background gradient of the small particles, then they would be expected to diffuse symmetrically, but any asymmetry can be measured and will be evidence of diffusiophoresis. Now I want to introduce you to another type of diffusiophoresis, since this will be important for interpreting the results of this experiment. Electrolyte-driven diffusiophoresis can occur when we have gradients of ions. It's a combination of two effects, electrophoresis and chemiphoresis. In electrophoresis, you might have heard the term before in the terms of, say, electrophoresis for separating out DNA fragments. This occurs when we have anions and cations at different size. And because they're different sizes, they diffuse at different rates. This in turn sets up an electric field between our cations and our anions. And this electric field can drive the motion of a nanoparticle with a surface charge. Chemipheresis occurs because the concentration of gradient of ions also means that there's an osmotic pressure gradient around each nanoparticle. This osmotic pressure gradient drives fluid flow along the particle surface and in turn drives the particle up the concentration gradient of the ions. So whilst chemipheresis always drives particles up the concentration gradient of ions, electrophoresis can occur in either direction, kind of depending on the size difference, the balance, and we get a combination of these two effects. Now I want to think about the question of what happens when one of the ions is much bigger than the other ion, say the cation much bigger than the anion, or the anion much bigger than the cation. In my experimental system, I've got a mixture of silica and latex particles. Now, the silica nanoparticles have a negative surface charge, and they're stabilized by sodium counter ions. The silica nanoparticles are much bigger than their stabilizing counter ions, and so the silica diffuses much slower. We can characterize the diffusion of the silica-sodium pair using the IMA polar diffusion coefficient, dA. Because of the theory of electrolyte-driven diffusophoresis discussed on the previous slide, we might be led to expect that the silica concentration gradient could drive the motion of latex particles with a negative surface charge. On this slide, I'm showing some equations that describe this process, starting with the silica and the sodium. On the left-hand side of the equation, we have the rate of change of silica and sodium concentration with time. And on the right-hand side, we have our diffusion term based on the amipolar diffusion coefficient. For the latex, the equation looks a little more complicated. On the left-hand side, we first have the rate of change of the volume fraction of latex with respect to time. On the right-hand side, we still have a diffusion term. Here, D2 is the diffusion coefficient of the latex particles, and these particles are quite relatively large, and so we could ignore this diffusion term. As that leads us to the remaining term, the diffusophoretic term. We see that this is driven by a diffusophoretic velocity, which is highlighted in red. We have a coefficient gamma 1, our diffusophoretic drift coefficient, and that's in front of the grad of the log of the total salt concentration. At gamma, our diffusophoretic drift coefficient, in the limit where we have many charges on each silica nanoparticle, we can write this equation for gamma, and we see there's a combination of contributions from electrophoresis and from chemipheresis. Now I'm going to show you some example experimental results. So you can see some images of the tank on the right of the screen. On the left is a schematic of how this experiment was set up. So the top layer is a thick layer of deionized water. Then there's a thin middle layer of latex dispersion, which looks milky to the camera. And at the bottom, there's a silica sodium dispersion, which the camera can't see. So you see from the photos that over time, the latex layer moves upwards, that is, down the concentration gradient of the silica. This is supportive of this being a diffusophoresis process. Now, I wanted to confirm what type of diffusophoresis was happening. And therefore, I added salt uniformly to each layer, so a kind of background salt concentration. Here I added 10 millimolar of KCl. That's because the background salt should shield the electric field, and it should affect our process if it's electrolyte driven. And indeed, you see that the upwards latex motion is arrested when we add our background salt. So it's supportive of it being an electrolyte driven process. Now I can analyze these images. So I convert the latex intensity in the image to an average, a horizontally average latex concentration. So you can see profiles for day 0, 1, 2, and 3. The one for day 0, that's in blue, you see that there's an initial peak concentration at a certain height up the tank, and over time the position of this peak moves up the tank. I can plot the position of the peak over time. I've fitted as a guide to the eye t to the half. From theory, we don't quite expect a t to the half. It's but it's more a guide to the eye, and it suggests it could be some kind of diffusive-phoretic process at the power of half. The silica solution could be an error function, and then the latex moves in the silica gradient. But t to the half is a reasonable approximation to the solution. So I repeated this experiment with the background salt concentration, varying the background salt concentration. I also did some different background salts. On this slide, I've plotted the latex peak position after 3 days against the reciprocal of the conductivity. And you see get a nice straight line, which is supporting that the diffusoretic flux is inversely proportional to the background salt concentration. And that's supportive. It is following the equations that I wrote down earlier. I'd like to compare these results with what we would expect from theory. The magnitude of the latex motion depends on the silica balance and the silica radius, which is why I've shown some different example results for different radii and different silica balances. And I've plotted the predicted latex front position against time. Perhaps qualitatively, it somewhat resembles the sort of t to the half shape that we saw earlier. But we also see that the magnitude of the predicted motion is similar, I mean, order a centimeter, which is similar to what we saw in the experiments. It's just having a quantitative comparison here is difficult because the silica nanoparticles aren't actually spherical. They form fractal agglomerates, like shown in this image. I therefore carried out more experiments using particles that were manufactured by Steve Arm's group in Sheffield Chemistry. They made us spherical particles with a known number of surface charges. I repeated the same experiments. I got very similar results. Perhaps our theory still slightly overpredicts the motion that we see experimentally. That's likely because my equations are valid for dilute solution and they don't account for hydrodynamic hindrance. This work is published here if you're interested. To summarize this section, we see a rising of the latex in the experiment, which is likely to be due to diffusiophoresis driven by the gradient in silica and its stabilizing counterion. This was also interesting as we learned that salt-driven diffusiophoresis is important even when one of our ions is a nanoparticle. It suggests that diffusiophoresis may be occurring where we hadn't previously occurred to us that it might. So now, having first given a bit of a basic model of drying films and then answering the question of what phenomena should I be modeling in a particular system, I'd like to put this together as to how we could use this to control particle arrangement in drying films. On this slide, I've outlined the kind of process that we go through in order to control the particle arrangement in the final film. We first want to identify the relevant phenomena, which could be done, say, by experiment, thinking about the physics and the chemistry of the particles. Then we want to model these phenomena. We can pick an appropriate method. I've been using continuum modeling. And then we want some way of assessing what stratification we've achieved. I've defined a stratification parameter beta, which is a difference in the average height up the film of the small and the large particles, and normalized that. So it's normalized such that beta equals 0 for a homogeneous film, and beta is +1 for completely small on top stratified, and conversely it would be -1 for completely loud on top stratified. I'm going to show you an example for the silica dispersion containing small amounts of latex, which would be similar to the experimental system that I showed earlier. I want to see what happens as we dry. We want to predict what might happen as we dry this. I consider what the relevant phenomena are. So diffusion, and from the experiment, we think a nanoparticle and counter-ion driven diffusiophoresis as likely the most important other phenomena occurring, and evaporation. I select some parameters. I'm going to vary the background salt concentration, since the experiment showed that varying background salt concentration can tune the strength of electrolyte-driven diffusiophoresis. And I picked some Peclet numbers, so I've picked order 1, so diffusion and evaporation are similarly important. As on this slide, I have some results. I'm going to plot the degree of stratification beta against the background salt concentration, kind of a normalized background salt concentration. So positive beta is small on top stratified, and negative beta is large on top stratified. I'm going to show some results for 3 different times. So at the earliest time, we get results in blue. And over time, the stratification grows. And what's interesting is that we see that at large K values, we're getting large on top stratification. Large K values means we've got large background salt concentration, so our electric field is being arrested, and we're pretty much going to get a diffusion-only solution, which is why we're getting large on top stratification predicted here. Then at small magnitudes of background salt, we're having a significant amount of electrolyte-driven diffusiophoresis occurring, and so we're getting small on top stratification predicted. And this plot is suggesting that by tuning the background salt concentration, we may be able to pick our final stratification. And I want to go back to the question of modeling the appropriate phenomena. This is the kind of picture that I had. The silica and latex particles, they have a certain radii, which we could vary. And they also have surface potentials. And these surface potentials depend on the pH and the end groups, which we could also vary. Because these are these are nanoparticles, we may also want to include other interactions, such as van der Waals interactions we may find to be important. In practice, it's not just the silica that would have counter ions. If our latex is negative surface charge, it would have counter ions too. Just if there's only a small amount of latex compared to the silica, we could ignore this. But if we have comparable amounts of each, we would need to include this in our model too. So I want to draw some conclusions. So I was trying to answer the question of how can we use mathematical modeling to control particle arrangement in drying films. I've shown that continuum models can give insight to what the important phenomena are. And particularly from the experiments I carried out, we learned that diffusiophoretic motion is important. I'm currently working on building a more comprehensive interactions model, measuring particle interactions. That's what I'm working on currently in my fellowship in Oxford. And then it would be cool to test these predictions against prototypes of dried films. And, thanks very much for listening. I'm very happy to take any questions.
Thank you very much, Claire. That was reminds me exactly of the BAMC talk and why you won. So I'm going to open up. I obviously always have questions, but I'm going to open up to the floor. So Joseph had a question, which was about the Peclet number, which was quite a long time ago. Joseph, do you want to come in and say something about your question?
Yes. Because from the slides, okay, it seems that the PE2 number was double that of PE1, right?
That was in all the examples I showed. It was, but the Peclet number. Remember that I defined it as a ratio of evaporation to diffusion. And for the diffusion coefficient, I was using the Stokes-Einstein diffusion coefficient, which was inversely proportional to the particle radius. And so the ratio of the Peclet numbers is equal to the ratio of the particle radii. And I just happened to show examples for a size ratio of 2, but you can vary the size ratio. Another parameter set you could vary.
It can vary the ratio. It can be, for example, 1:3, for instance.
Yep. It probably can't be like, I don't know, 1 to 1,000, because we might find the big particles then aren't still colloidally stable. But yeah, within any kind of sensible range, you can vary the size ratio.
All right. Because I thought that it is always double, right? But not necessarily the case.
I think I was interested in exploring effects of other parameters, but it would be interesting to explore the size ratio too, particularly if you're looking at, say, excluded volume diffusiophoresis.
Okay. All right. Thank you.
Thank you very much, Joseph. Does anyone else have questions then before I jump in with one to get the conversation started? Feel free to put your hands up then if you do, and or write them in the chat. So my first question was, right at the beginning, you said that molecular dynamics are quite hard to solve. Do you want to comment on that a little bit as to why that is?
But by hard, I mean computationally difficult, as in would require a lot of computer power if you want to model conversely, you might be limited by your computer power as to how big a system you're going to model. Because you need to model every single particle, and these particles are quite small, you're going to have a very large number of particles in a small amount of space. It might be important at each time step. It'd be important where all the particles are and how they interact with the other particles up to a distance at which they might stop interacting.
Yes. Yeah.
As a result, there may be also many equations. There's equations for each particle, so it becomes a big system of equations to solve.
Yes, I imagine that adds some extra complexities as well that you may not want. Like you have to make sure the particles don't merge and things like that. I can see it getting quite complicated quite quickly.
Yeah, also to think carefully about, say, what's happening at interfaces.
Yes. Yeah, and that's computationally quite challenging. And so, okay, that's fine. And how are you solving like the numerical scheme? Are you using just finite elements?
I started off trying a finite difference method. It was okay. It didn't work so well at high Peclet number. At high Peclet number, you saw I had results which showed very sharp, steep fronts, and then you get very large gradients at that point, and it would blow up quite easily unless you had very, very small space steps and also small time steps. And then changed to a finite volume method. It still has a bit of a difficulty at high Peclet number, and you still need to make the resolution even better. But it was much better at conserving particle mass.
Yeah. I mean,
because particles go from one volume to another volume, so you can't lose them. This is
precisely what the finite volume method was sort of made for. This type of work. So this is all two-dimensional then. Or is it? Yeah, it's it's one-dimensional.
What one-dimensional? As if you've got a very large space that you were coating, I suppose you could approximate it as one-dimensional, as in edge effects not being important. Although there could be flows set up in the transverse direction, perhaps.
Is this something that you might consider in the future, extending this to multiple dimensions?
If you have a molecular dynamics model, it's inherently got another dimension in it, because the particles are of finite size. I mean, so at some point, might want to add another dimension to it. I think first might want to address. I want to address what I think the most important phenomena are. But I suppose it is a question: is another dimension important?
Yes, that is a very good point, rather than doing it for the sake of it. So Jack has a question. Jack, do you want to come in and say always like me? Jack is staying muted, so I guess that signals me to read his question. So in the chat, Jack has said in his field, there is a similar question about modeling paradigms between kinetic, so particle and fluid models. What do you lose in using continuum models? That's a good question.
It's a good question. I've been doing some work comparing my continuum model to a molecular dynamics model. I mean, for the comparison to be valid, the models in the first place have to do their best at modeling the same physics, so the same interaction potentials and same particle sizes and so on. When you have a continuum model, you need to be you're trying to come up with equations that still incorporate the physics model and the molecular dynamics, so that they don't lose that accuracy, and they probably inherently will lose some accuracy. It can be challenging writing expressions, continuum model expressions that are accurate at higher concentrations, whereas in molecular dynamics, so you just define how the particles behave. So they probably have less of that difficulty as you increase the concentration.
Mm-hmm. Yeah.
I suppose we need to do both, both really, to check the accuracy of the continuum models with the molecular dynamics models, and then you have and then take advantage of your continuum model being easy to solve. And
I hope that answers your question, Jack. There we go. Very good. Does anyone else have any questions, or am I going to fire another one away, which is a chemistry question, I think? Since I haven't seen any hands, I'll go with this one. So forgive me for my layman understanding of chemistry. It's not even layman, it's probably worse than layman. But why the experiments you want to use using like salt, silica, and latex? Is there something particular about this combination? Is it because it's easy experimentable, or like what is it that's so attractive about these things for this work?
From a practical perspective, they're cheap, and also because they're cheap, they're commonly used in industrial coatings. So I wanted to use some particles that were relevant to real coatings. I suppose you could have also gone for model hard spheres if you really wanted to compare to the excluded volume diffusive modeling. When I carried out first carried out experiment, I actually wanted to vary the size ratio between the silica particles and the latex particles. I quickly found that the size ratio didn't really matter very much, because it wasn't excluded volume differesis that was important in this particular system. It was the charges. Still more to learn about things that could be relevant to industry. I mean, rubber gloves and latex gloves and.
Makes sense to me. Yep, industry driven. Yep, makes complete sense, and cheap. We do like cheap in industry.
And in the lab.
Yeah, and the lab.
Doesn't matter if you waste a load of it.
Yeah, definitely a lab. So I mean, leading on from that, with this in mind, when do you do experiments to find out certain parameters for your system, or are these things that are well known now in the literature? So I was thinking about like some of the diffusivity constants and some of these bits and bobs. Like, how do you find those? Are they experimentally driven? Are they mathematically driven and assumed? Like, what's the process that you need?
The particles are spherical. From the Stokes-Einstein diffusion coefficient isn't bad. But when the particles become non-spherical, it becomes more difficult. And then when the non-spherical dimensions can become important. The packing of the particles becomes important. If you want to measure the diffusion coefficient, and also how the sedimentation coefficients, how the mobility of particles changes as it becomes more concentrated. You can do that in a kind of centrifuge type experiments. So they're a way to measure the hydrodynamic hindrance. So we often modify the sedimentation coefficients could be viewed as a modification of a diffusion coefficient, so due to shape and concentration. So you can measure that experimentally, and then there are some fits people have made from having done these experiments. In terms of charge type things that they might be approximated. That I suppose sort of simple model. But I'm keen to measure particle interactions in my current work, because we often approximate particle interactions because they aren't being measured in, say, industry. They're formulations for personal care products and so on.
So experimentally driven. Okay. I mean, that's all my questions now. Jack is coming in, not Jack Reed, Jack Ingham is coming. So Jack, do you want to unmute and pose your question, or would you like me to?
I'm happy to
Go ahead.
happy to pose the question.
Yeah,
just leading on from what you were saying about latex is a very cheap and ready available material to test. Does that mean that you have other ideas about other other materials, other substances that you could use in future, but lacking availability or cost barriers, stuff like that? Is there other experiments that you could build on top of this?
I'd like to do experiments where electrostatic effect, electrical interactions are not important, but it could have been changing the solvent to something like hexane, something non-polar. That creates experimental difficulties. It's so much safer to use water. I'd like to do experiments with things that behave as hard spheres, so I can compare to the excluded volume diffuser phoresis model. It'd be interesting. I do some work on batteries. You get dry films in batteries, and there's an important part of the battery production process, as the companies want to dry very quickly, but that ends up depositing the binder not very uniformly. So that would also be cool to compare to models, but again, that's industrially driven.
Mm.
So could I also ask then? So does it mean so you have to physically do the experiment as a real world setup, or could it be something that you could simulate or kind of run computationally before you try these exotic materials or whatever that might necessarily not be safe or too expensive, etc.? Are there other methods you could look at?
In the case of something that's industrial driven, people make batteries, because it's someone we're making the things to compare with. My work, it would be theory and modeling inspired as to what to look at. So it reduces the number of experiments to do if you've done some modeling first. Don't necessarily have to do experiments of drying films as the first step. When you do experiments, so I did an experiment in a Healy-Shaw cell because what was important was how particles of different sizes move around each other in dispersion, and then the drying film is just adding evaporation to it. And evaporation is perhaps quite easier to model than the particles moving around each other. So we can understand the particles moving around each other a bit in different geometries to a complicated drying film.
I guess another one of these is something exotic. Even if it's your computer simulation, is that you may not know some of the parameters which are being found experimentally as well. So that might be another issue.
Yeah, that can certainly be the case, and we end up with more complicated mixtures of different ions. Meant to do clever experiments to try to extract the parameters. We might want to first know, are these parameters important? What's the sensitivity to them?
Yes. Yeah. Thank you very much. That was a great question. I don't know if you have any follow-up.
No. Thank you for the talk. Very interesting. It does open up a lot of potential things that you could think about. Off an innocuous initial subject, it does open up a lot of other avenues. You keep yourself busy for a long time looking into it.
So it's quite nicely, Claire. Okay, does anyone else have any questions? And if not, then I'm sort of happy to call that one for the night. Not seeing anyone pop up in the chat or anything. I'll let someone, maybe someone's typing. Give it a moment. I think we're all good. So in that case, again, we'd like to thank Claire very much for the talk and for you all to sort of joining us at 5 p.m. on a not so sunny Wednesday evening. Our next seminar will be sometime in January. We will be advertising it hopefully in sometime in November, so keep your eyes peeled for that one. It's likely to be on epidemics. So from me and the ECMs, thank you very much for coming. And like I said earlier, if you have any questions about what the ECM does, who we are, how you can get involved, then please send me an email. And again, thank you very much, Claire, and we'll stop it there.